Have you ever stopped and wondered what's really going on inside a computer processor? I mean, deep, deep down. Let's forget about software and operating systems for a minute. Today, we're going to crack open the chip itself and look at the tiny, elegant machinery that makes everything, and I mean everything, possible. All right, let's get into it.
So, what are we even looking for in there? If you could smash a CPU into its tiniest, most basic parts, what would you even find? Well, it's probably not as complicated as you're thinking. In fact, it all boils down to just three really essential jobs.
And here they are. It really just comes down to this: storing a little piece of information, moving that information from one place to another, and counting. That's it. These three simple functions are the foundation that all of modern computing is built on. So let's tackle the first one: storing data.
To store data right where the action is, a processor uses something called a register. You can think of these as the CPU's own personal, super-fast, short-term memory.
And you know, the concept is actually pretty simple. At its core, a register is just a collection of tiny electronic switches called flip-flops. Each one of these little guys can store a single bit, a 0 or a 1. So if you group, say, 4 of them together, you get a 4-bit register. Now it can hold a number, like 1111.
This analogy is just perfect. Picture a tiny little box that can hold one piece of info. A register is just a row of these boxes, all lined up, working together to hold a complete value right where the processor needs it most. But how does the processor know when to actually put something new into the box? And that is the key question, right? Because there's data flying around constantly inside a chip. If the register just grabbed whatever was at its input at any random moment, it would be total chaos. It needs a trigger, a signal that basically yells, "Okay, store what you see now."
And that trigger is the clock. The system clock is literally the heartbeat of the entire processor. It sends out this perfectly steady pulse over and over. A register only pays attention and stores new data at the exact moment that pulse arrives. Absolutely nothing happens without the clock's permission.
Okay, let's walk through this so you can see what I mean. In step 1, the input is 1011. But see, the clock is off, so the register just ignores it. The output stays the same. Then, in step 2, bam, the clock pulses. You can see it with that little up arrow. Instantly, the register grabs the 1011 from the input and stores it. Now here's the cool part. Look at step 3. The input changes to something else, but because there's no new clock signal, the register just holds on tight to that 1011. It proves the point. The clock signal is king.
Okay, so we've got storing data down, but that's not super useful if the data's just stuck in one place, right? We need a way to move it around. And that's where our second building block, the shift register, comes into play.
A shift register is a really clever twist on a normal register. It does the same basic job of storing bits, but it has this awesome superpower. With every single tick of that same system clock, it can shift all of its contents one spot over.
This is such a great way to picture it. Imagine 4 people standing in a line. The first person gets a ball. When the whistle blows, that's our clock pulse, they pass it to the person next to them. Then the whistle blows again, and that person passes it to the third, and so on. The data is literally moving down the line, one position at a time, all in perfect rhythm.
Let's see this thing in action. We start with the number 1011. Okay, after one clock pulse, everything shifts one spot to the right. The last one at the end kind of falls off, a new 0 gets added to the front, and now we have 0101. Another clock pulse hits, and it happens again. Now it's 0010. So you see, we are actively moving data, bit by bit, all perfectly controlled by that relentless clock.
All right, so we can store data and we can move data. But how does the processor keep track of what to do next? How does it follow the steps in a program in the right order? For that, we need our third and final piece of the puzzle, the counter.
So the counter's job is just beautiful in its simplicity. It just counts. For every single pulse it gets from that system clock, it just adds 1 to its value. It's the metronome. It's the pacemaker that lets the CPU run through instructions in a precise, orderly sequence. Without this, a computer program would just be a chaotic mess of commands.
This is the perfect mental image. You know, just like hitting the button on a score counter to add a point, the counter circuit sees a clock pulse and bam, it adds 1. This simple little mechanism is what lets a program go from instruction number 1 to instruction number 2 to instruction number 3. That step-by-step process is how literally everything happens on your computer.
So let's see how this works in the binary world. A simple 2-bit counter starts at 00. The first clock pulse arrives, and it ticks up to 0, 1. The second pulse comes in, it becomes 1, 0, which is just binary for the number 2. The third pulse makes it 1, 1, that's 3. And on the fourth pulse, it's full. So it rolls over right back to 0, 0, ready to start the count all over again. It's just counting, one pulse at a time.
Now, a quick but important side note. There are two main ways you can build these counters. An older, kind of slow design is called asynchronous, where the clock signal sort of ripples through the circuit one bit at a time, which can cause delays. But in any modern chip, they use what's called a synchronous design. This means every single part gets the clock signal at the exact same instant. It makes them way faster and much more accurate, which is absolutely essential for the processors we use today. So let's take a step back and put all these pieces together. We've looked at three things that, on their own, seem pretty simple, right? But when you combine them, well, that's when you get something truly extraordinary.
So here's the big picture. Registers are the CPU's internal scratch pad, holding the data it's working on right now. Shift registers are like the internal highways, moving that data exactly where it needs to go. And counters? They're the conductor of the orchestra, controlling the timing and the sequence of every single operation. These are the gears that make the digital mind turn.
And that really leads to one last thought, which I find so amazing. We've just seen how the simple, almost boring actions of storing, moving, and counting are enough to build the brain of a computer. So it just makes you wonder, what other incredibly complex systems, whether in technology or even in nature, are built on a foundation of just a few stunningly simple rules?